A Boeing 787 is a staggering piece of engineering, weighing roughly 230,000 kilograms. To put that in perspective, that is the equivalent weight of about 38 African elephants. It's a massive metallic contradiction. I mean, how does something that heavy actually stay in the air? The answer lies in the physics of lift. While objects lighter than air, like balloons, can stay aloft effortlessly, heavier objects require a specific force to combat gravity. This force is primarily produced by the wings. A plane takes off the moment the upward lift force exceeds the downward pull of gravity. Now, this is a constant battle between four forces: lift, weight, drag, and thrust. For the plane to climb and remain airborne, lift must effectively cancel out the weight. But here's the real question. How does a wing actually create this invisible support? To understand how a massive aircraft stays aloft, we have to fundamentally shift how we perceive the air around us. Most of us think of air as empty space, a void we move through. But in physics, air is a fluid medium. It behaves like water, only with a much lower density. Imagine the air not as nothingness, but as a dense sea of molecules that can be pushed, bent, and compressed. It's a strange thought, but we are essentially living at the bottom of a vast, invisible ocean of air. When a wing cuts through this medium, it isn't just sliding through a vacuum. It's physically colliding with billions upon billions of air molecules. Flight begins here, not in the void, but in the physical displacement of a fluid that is simply too thin for our eyes to see. Even the most brilliant minds in history have struggled with the complexities of fluid dynamics. Take Albert Einstein, for example. In 1917, Einstein attempted to design an airplane wing based on an incomplete theory of flight. He wasn't just scribbling equations on a chalkboard, he applied his logic to a physical structure. He developed what became known as the catback wing design, which featured an extreme, exaggerated level of curvature. On paper, the mathematical symmetry seemed sound. However, the atmosphere had other plans. When the design was finally put to a physical test, the results were far from graceful. A test pilot reported that Einstein's wing caused the plane to wobble and sway like a pregnant duck in the sky. It's a humbling reminder that in aerodynamics, a beautiful equation does not always translate into a stable flight. And we're about to discover exactly where his logic failed and why that specific curve turned a masterpiece of physics into a clumsy, wobbling disaster. Now, here's where most textbooks get it wrong. You've likely heard the longer path or equal transit time theory, which is a common but debunked explanation for lift. This theory claims that air molecules traveling over the curved top of a wing must meet the molecules traveling underneath at the exact same time at the trailing edge. It sounds logical. Since the upper surface is longer, the air must speed up to catch up with its partner. But this is a persistent misconception. In reality, air molecules passing over the top reach the back of the wing much faster than those passing underneath. They don't wait for each other. They have no coordinated plan to meet. The molecules move independently. Once we accept the fact that the air on top moves faster without the need to synchronize, we realize that the equal transit requirement is a complete fabrication. So let's look at the actual physics of the air. When air contacts the solid surface of a wing, a thin layer of air actually sticks to the surface. This isn't just a slide, it's a physical grip known as the boundary layer. As the plane moves, air directed upwards is subjected to centripetal acceleration as it curves toward the nose of the wing. This forces the air to follow a curved path. Because of this, the air above the wing gains significantly more acceleration than the air below. This brings us to the realm of pressure. When the speed of air over the wing increases, the pressure it exerts on the wing decreases. This creates a pocket of low pressure on top, while the pressure on the lower surface remains higher. On a wing with a flat bottom, the slower moving air maintains a higher pressure. This is where Bernoulli's principle becomes a tangible force. The pressure gap between the upper and lower surfaces results in a powerful upward push. High air pressure from underneath essentially shoves the aircraft upward, supporting the weight of the plane. It's a simple matter of balance. The air is being deflected downward, and therefore the wing is pushed up. But there's a hidden detail at the back of the wing, the sharp edge, that makes this entire system possible. This creates a fundamental tension in aviation physics. On one side, you have the Bernoulli principle, focusing on the pressure difference, and on the other, Newton's third law, focusing on the air being pushed down. For decades, people have argued over which is the correct explanation. But the truth is, they're simply two different ways of describing the same physical event. To get a truly precise picture, engineers use the Navier-Stokes equations to model the airflow and detail the formation of lift. This mathematical framework doesn't rely on a single law. It combines several complex elements. It integrates free stream velocity, the line vortex model, and the principle of flow tangency. It also relies on the Kutta condition and the Kutta-Joukowsky theorem to explain how the air actually leaves the wing. When these elements align, the result is a powerful upward force. The magnitude of this lift increases as the airplane's speed and the pressure difference increase. It's a linear relationship. More speed and a wider pressure gap equal more lift. But to understand why the air doesn't just swirl around the back of the wing, we have to look at a very specific geometric detail. This is the tiny detail that engineers spend years studying, but almost no one mentions in introductory videos: the Kutta condition. Named after Martin Kutta, a German mathematician, this principle applies specifically to solid bodies with sharp corners, like the trailing edges of airfoils. According to experts like Kuth and Schetzer, a body with a sharp trailing edge moving through a fluid creates a circulation strong enough to keep the rear stagnation point exactly at the edge. In this flow pattern, fluid approaches the corner from above and below, meets precisely at the point, and flows away. None of the fluid curls back around the sharp corner. For this to work, the circulation of the flow must be a specific value determined by the airfoil shape, the angle of attack, and the airspeed. This Kutta condition is used with the Kutta-Joukowsky theorem to quantify the lift force, linking the abstract concept of circulation to a physical push. But how does this state actually begin? Well, when a wing with a sharp trailing edge starts moving at an angle, the two stagnation points are initially mismatched. Air passing the underside must flow around the trailing edge and along the topside. However, the high airspeed at the edge causes strong viscous forces to act on the air. These forces create a powerful vortex that accumulates on the topside near the back of the wing, known as the starting vortex. Early aerodynamicists even photographed these vortices in liquids to prove they exist. According to Kelvin's circulation theorem, the vorticity in this starting vortex is matched by the bound vortex of the airfoil. This ensures a constant total circulation, providing the final piece of the puzzle. The air leaves the wing smoothly instead of swirling back. Looking at these different explanations, it feels like the ancient parable of the blind men and the elephant. Each person touches a different part of the wing's interaction with the air and describes a different truth. But lift is not a single, isolated mechanism. It's a unified phenomenon. It extends meters beyond the wing surface, where air is swept up and down, and it's shaped by vortices at the wingtips. These wingtip vortices aren't just waste, they're an inherent part of the lift generation process. The physics is a complete, interconnected system where pressure, momentum, and circulation all work in unison. If you think wing curvature is the only way to fly, you're mistaken. Curvature does not cause lift. A flat wing tilted upwards can also generate lift if the air is forced to bend around it. The secret is the angle of attack, the angle at which the wing meets the oncoming air. This is the primary driver for lift. When a plane maintains a positive angle of attack, it pushes air down, regardless of the wing's specific shape. However, there is a limit. Too much curvature or too steep an angle causes the airflow to become turbulent and separate from the surface, leading to a stall. It's a striking contrast in scale. Just as a global hotel chain like Marriott manages hundreds of properties with precision, a tiny change in a wing's angle can dictate the entire outcome of a flight, from a smooth ascent to a sudden drop. Flight is a masterpiece of contradictions. We start with a Boeing 787, a machine weighing as much as 38 African elephants, and we find that its survival in the sky depends on things we cannot see. It depends on a thin layer of air sticking to a metal surface, a low pressure pocket forming over a curved wing, and a sharp trailing edge ensuring that air leaves the wing smoothly via the Kutta condition. Whether you describe it through the lens of Bernoulli's pressure or Newton's downward deflection, the result is the same: a massive object defying gravity. The comforting irony is that while scientists and textbooks may argue over the mathematical labels and the correct theory, the physics of the air remains constant and reliable. The planes keep flying because the atmosphere doesn't care about our definitions. It only obeys the laws of fluid dynamics. But as we push toward hypersonic speeds and new wing designs, will these classic laws be enough, or are we still like the blind men, only touching one part of the elephant?